All right, everybody. If you're one of the 5 students who have not yet logged into the Desmos activity, please do so as soon as you can so that you can follow along and participate. So again, thank you for those of you who checked in. I'll take a look at all those responses after class when I have time to actually read them. For now, we're going to get started with our lesson. So we're going to get the second screen available here. If you want to follow along on the shared screen, you're more than welcome to, or go ahead and click into the second screen that is now open. All right, so our objectives for section 9.2, which is tests about a population proportion. All right, we need to be able to state and check the random 10% and large counts conditions for performing a significance test about a population proportion. These are the same 3 conditions that we had to check before finding a confidence interval in chapter 8. We need to be able to perform a significance test about a population proportion. We need to be able to interpret the power of a test and describe what factors affect the power of a test. And we need to be able to describe the relationship among the probability of a type 1 error significance level, probability of a type 2 error, and the power of a test. Right. We will not get to all of this today, but we will eventually. So that's what we're working on today. So first, just like in chapter 8, we introduced 3 conditions that should be met before we construct a confidence interval for an unknown population proportion. Random, 10% when sampling without replacement, and large counts. These same 3 conditions must be verified before carrying out a significance test. All right. So again, we have the same 3 conditions now called the conditions for performing a significance test about a proportion. It must be random. The data come from a well-designed sample, random sample, or randomized experiment. 10% condition must be met when sampling without replacement, which means we have to check that the sample size is less than or equal to 10% of the population size. And we have to check the large counts condition, which says that the number of successes and the number of failures are both at least 10, or n times p, and p sub 0 in this case is the null hypothesis value for the proportion. And so n times p sub 0, n times 1 minus p sub 0, both need to be at least 10. Those are 3 conditions, same as for confidence intervals. Okay, random, 10%, large counts. If you'd like a moment to write any of this down for your notes, can you please raise your hand? Okie dokie. So then we get to our first exercise, walking to school. A recent report claimed that 13% of students typically walk to school. Deanna thinks the proportion is higher than 0.13 at her large elementary school. So she surveys a random sample of 100 students to find out. Are the conditions for carrying out a significance test met, yes or no? Make your selection and then explain why you made that choice. All right, the explanation box will pop up after you select yes or no. All right, guys, let's talk about this one. So we seem as a class, most of you guys selected yes. We had a few students who said no. Based on simply checking our conditions, random, 10%, and large counts, right? And not anything else. Like we're not checking to see like if we'll have sampling errors, so to say, right? So just based on checking conditions, do we have enough? Are the conditions met? Yes, they are. And let's look at why. Where did I put this? There. Too much. There we go. So here is the checks, so to say. Was it random? Yes, the sample is a random sample, so that condition's been met. Right, 10%, the sample size of 100 is less than 10% of the school's population. We're assuming that. We're told the school is large. We're not given the actual number. So for the purposes of what we know, we're going to say, well, we're going to assume that 100 is less than 10%. We're going to say that there's probably more than 1,000 students in this school. And large counts, right? 0.13 times 100 is 13, which is greater than or equal to 10, and 0.87 times 100 is equal to 87, which is also greater than or equal to 10. So the large counts condition has been met. Our three conditions are good. We are okay to proceed and do a test. All right. So anything clarify about checking conditions? So then, let's look what happens next. So what is a significance test? Right. A significance test uses sample data to measure the strength of evidence against the null hypothesis. Right. Here's some basic principles that apply to most tests. The test compares a statistic calculated from sample data with the value of the parameter stated by the null hypothesis. Values of the statistic of this far from the null parameter value in the direction specified by the alternative hypothesis give evidence against the null hypothesis. Right, so essentially think of like your normal curve and the null hypothesis is the center. Values that end up way out on the tails on either side, right? If our sample values end up way out on the tails, that's evidence saying that, well, maybe the middle of this isn't at the null hypothesis. Maybe it's something else, right? When things are relatively close to that value, then we're okay, right? We don't necessarily have evidence against it. Right, and then we get a test statistic measures how far a sample statistic diverges from what we would expect if the null hypothesis were true in standardized units. That is, test statistic equals statistic minus parameter divided by the standard deviation of the statistic. Right, and this is very similar to kind of the stuff that we used in chapter 8 for our confidence intervals. All right. So anyone need a moment to write anything down from this screen? Please raise your hand. All right. So then we have the Z statistic, very similar to a Z-score, but using our statistic and our hypothesis. When carrying out a significance test about a population, we will use the test statistic of a Z statistic. We call it a Z statistic because it is similar to a Z-score, and will be used along with table A to help find the p-value for our significance test. The Z statistic is Z equals p hat minus p divided by the square root of p sub 0 times 1 minus p sub 0 divided by n. Right. And again, I messed this up, but where p hat is the sample proportion, p is the parameter value, and p sub 0 is the null hypothesis parameter value. Typically, p and p sub 0 are the same value. So this is our Z statistic. And I'm actually going to move to the next slide because I have this formula there again, so I'll be able to get that copied down, but it comes along with a little more information. Right, so we have the one sample Z test for a proportion. Right. And this is our inference method, as we could call it, for testing, right? Doing significance testing. One sample Z test for a proportion. Choose an SRS of size n from a large population that contains an unknown proportion p of successes. To test the hypothesis, null hypothesis such that p equals p sub 0. Compute the z statistic, which is what we saw on the previous screen. Z equals p hat minus p divided by the square root of p sub 0 times 1 minus p sub 0 divided by n. Find the p value by calculating the probability of getting a z statistic this large or larger in the direction specified by the alternative hypothesis h sub a. Right, so if our alternative is that the true proportion is greater than the null hypothesis, we're looking at the area under the curve to the right of z. If the alternative is that the proportion is less than the null hypothesis, we're looking at the area under the curve on our normal curve less than z. And if it is simply that it's just not equal to, in which case we have a two-sided alternative, we look at what is less than the z-score, the negative z-score on the left side, and what's greater than the positive z-score on the right side. We get a two-sided test. And essentially the z and curve here is the standard normal curve with our z-scores, and we'll be using table A. Can you raise your hand if you'd like a moment to write anything down? So that brings us to our next question, which refers back to the first question we saw on screen 4, walking to school. Now we have some sample data. We're going to refer to screen 4 for the original context, and then we have that for Deanna's survey, 17 students in the sample said they typically walk to school. Right. For A, we want to calculate the test statistic, and for part B, we want to find the p-value using table A. I do have a link to table A right here that you can click on. Hopefully that will take you to the entire formula sheet and tables that you can use. Table A is in there. For part A, you will be using the z statistic formula. And for part B, you're going to take that z value, that z score, and find it on table A. The thing you need to go back to the first part of the problem for is to determine what is the alternative hypothesis. Are you looking for the area under the curve greater than the alternative or less than the alternative? Right. It says here that Deanna thinks the proportion is higher than 0.13. So the alternative is that p is greater than 0.13, right? Which means you'll be using the area under the curve greater than whatever z value you find. Make sure you do your calculations accordingly. I'm going to give you guys, I'm going to start with 5 minutes on here. I do recommend one way to do this that might be a little easier is just write your work down by hand, take a picture, upload it here to Desmos. If that doesn't work, you're more than welcome just to type in your responses into the text entry window. All right, everybody. We're going to talk about this. I know that there may not have been enough time for some of you guys to finish the problem. That's totally okay. This is just practice and an opportunity to, see what we can do. If you didn't know exactly what to do, that's fine. We're going to go over it. I would highly recommend taking some notes on how we do this. So let's look at the work that goes with this. All right, so part A, calculating the test statistic, the z statistic, right? I have here first just the formula, z equals p hat minus p divided by the square root of p sub 0 times 1 minus p sub 0 divided by n. That's just a habit that I have. Anytime I use a formula, I like to write it down in its general form first, and then I substitute all of my values, which I have listed here. So we have my two hypotheses, right? H sub 0 where p equals 0.13 versus the alternative where p is greater than 0.13. Our sample proportion is 17 out of 100 or 0.17. And then p equals p sub 0, which is equal to 0.13. So then I substitute my values appropriately into the z calculation here, get 0.17 minus 0.13, right, divided by the square root of 0.13 times 0.87 divided by 100. This gets us a test statistic, the z statistic of 1.19, approximately. Right, we round a little bit. Right, so that's how we calculated our test statistic. Is there any questions about this part of the process? Any questions about where the numbers came from, anything? All right. So then part B, we want to find the p-value. All right, our p-value, right, is the probability that z is greater than 1.19, right, because our alternative is for greater than. All right, again, table A does not provide us proportions under the curve that are greater than a certain z value. They only provide less than. All right, so I always forget the name of this rule, but we use this rule where we can subtract the probability that z is less than or equal to 1.19 from 1 to get this. I think it's a complement, something like complement rule. I always forget what it's called, but I use it all the time. So we have 1 minus the probability of z being less than or equal to 1.19, because that one I can find on table A. Right? When we go into table A here, we find 1.1 on the left-hand side, 0.09 on the top column, the top row. They intersect at 0.8830. I subtract that from 1, we get 0.117, or about 11.7%. All right. On the normal curve here, this is the proportion that I found, this shaded red area. Right. The proportion of the curve that's in this area, this shaded part, is 0.117. Right. And we provide the illustration to kind of show, like, visually, we know that we're looking for the greater than proportion, and that proportion should be, I mean, at the very least, less than 50%, right? Because 50% would be at 0. So if you got a solution for the p-value that doesn't really match the part of the graph that's supposed to be shaded, you may have made an error. Right? Is there any clarification I can give on this part of the process and finding our p-value? All right. So as far as this problem is concerned, we're done. We were not asked to make a conclusion about anything. We were just simply asked to calculate the test statistic and find the p-value. Right, so there's nothing more for us to do with this problem. Okay. All right, so moving on. We now have, what we just did was a one-sided test. We can also have a two-sided test, all right? And this involves the alternative where we're just not equal to the null hypothesis. Right, the p-value in a one-sided test is the area in one tail of a standard normal distribution, the tail specified by the alternative hypothesis. That's what we just saw. In a two-sided test, the alternative hypothesis has the form h sub a such that p is not equal to p sub 0. Right, we're just saying the true proportion is not equal to the null hypothesis proportion. The p-value in such a test is the probability of getting a sample proportion as far as or farther from p sub 0 in either direction than the observed value of p hat. As a result, you have to find the area in both tails of a standard normal distribution to get the p-value. Right? Which means if we look back at our picture on screen 7, right, we have our one-sided test, or the first two curves. The two-sided test is this last one where we get a z statistic and we find the area under the curve that is less than the negative z, all right, the negative value of the z statistic, and what's greater than the positive z value. We have to add those two areas up. The good thing is that we have symmetry, so if we find one, we just double it, and we have the p-value. Okay, so that is the major difference between a one-sided and a two-sided test. All right. So we need a moment to write anything down for their notes. All right. So then there is a link between confidence intervals and two-sided tests. All right. The 95% confidence interval gives an approximate range of p sub zeros that would not be rejected by a two-sided test at the alpha equals 0.05 significance level. Right, so the confidence interval tells us, okay, these are all the things that are plausible, which would lead us not to reject the null hypothesis. The stuff on the tails in a two-sided test is outside of our confidence interval, which would lead us to reject the null hypothesis. A two-sided test at significance level alpha, say alpha equals 0.5, and this is common. If you're not told the significance level in a problem context, use 0.05, sorry, 0.05. And a 100 times 1 minus alpha percent confidence interval, 95% confidence interval, if alpha equals 0.05, gives similar information about the population parameter. Right? Meaning if I know like the z parts that are too extreme, then I can also kind of make an inference about what's plausible, assuming the null hypothesis is true. Is there anything I can clarify about this? All right, and then now that we have all the little parts and pieces here for our significance test, we get the four-step process for performing a significance test. Right, to perform a significance test, we state hypotheses, check conditions, calculate a test statistic and p-value, and draw a conclusion in the context of the problem. The four-step process is ideal for organizing our work. Right, and so this is the four-step process for a significance test. This works for proportions and means. There's not a separate one for means. So state, what hypotheses do you want to test and at what significance level? Define any parameters you use, right? Make sure that whoever you're writing this for knows that you're talking about a population proportion, that's what P represents, or population mean, that's what mu represents, right? Plan, choose the appropriate inference method. In this case, we're doing the one sample z-test for population proportions. Check conditions, random, 10%, large counts. Do, if the conditions are met, perform calculations. Find the test statistic, or compute the test statistic, find the p-value. And finally, conclude, make a decision about the hypotheses in the context of the problem. The conclusion is where you make your statement about because the p-value is greater than alpha, right? We failed to reject the null hypothesis. We do not have convincing evidence of the alternative. Or because the p-value is less than alpha, right? We reject the null hypothesis, and we do have convincing evidence that the alternative, we do have convincing evidence for the alternative hypothesis, right? And then we just fill that in with the like specifics from our context. Okay. So this is our four-step process. It helps you organize your work and it makes sure that you cover all the parts that they're going to check for on the AP exam. Is there a moment to write anything down? All right. Excellent. Okay, so we're gonna stop here as far as the Desmos activity goes. There is a little bit more. We'll get to that after break, essentially, which will be good because we'll have to review this anyway. I'll leave this kind of set to stop here. You'll have access to all the previous screens. While I have you on here, we're going to take a look at the course real quick. All right, so in March, obviously, today is 135, tomorrow is 246. Don't go to your 135 classes tomorrow. It's a 246 day tomorrow. There'll be a link here for the Desmos activity. I also have the PowerPoint presentation, like the one that I would do if we got today and tomorrow. That's just the presentation from the textbook, and it covers all of the things in the objectives. I'll post the work solutions to our Desmos problems later, and the recording will go here. Also, the notes, resources, and practice problems and solutions for 9.2 and 9.3 are all available. All right, I highly recommend taking a look at the practice problems for section 9.2 and 9.1 if you haven't taken a look at those, to get a little bit more familiar with the skills and concepts of significance testing. The Chapter 9 assessments are not ready yet. We're just not quite ready for them. I'll probably get those ready over spring break so that they are up and available once we come back. But for now, I don't want you guys worrying about them. And that is about it. If you guys have any other questions, comments, concerns, you need help with anything, please make sure to let me know. I'm happy to help. Send me a message, send me an email, whatever. Let me know you need help. I will help. Other than that, I won't see you guys for like 2 weeks, right? It'll be 2 weeks after spring break is over. I'll see you on Tuesday the 6th, I think it is, for regularly scheduled classes. And other than that, have a great rest of your day. Have a wonderful rest of your week. Enjoy your spring break. Have an awesome weekend, and I'll see you in a couple weeks.